Have you ever watched a great athlete and just wondered, how do they do that? Well, it's not just raw talent or endless training. It's physics. Turns out every incredible jump, every powerful throw, every dizzying spin is actually speaking a secret language. Today, we're going to learn that language and unpack the real science behind peak performance.
I mean, just look at this high jumper. They're practically flying. It looks like they're defying gravity itself. So how does that happen? That's the big question we're going to tackle. And trust me, by the end of this, you won't just see an amazing athlete. You'll see a beautiful physics experiment in action.
Okay, but before we can get to this soaring high jumper, we've got to build our foundation. We need to get the basic rules of motion down first. Think of this as our essential toolkit for understanding everything that comes next.
All right, let's clear up a couple of words we tend to use interchangeably: distance and displacement. See, distance is simple. It's just how far you went. You run a 400-meter lap, your distance is 400 meters. Easy. But displacement, that's different. It cares about where you started and where you ended up. So after that 400-meter lap, you're right back where you started, which means your displacement is 0. It's all about direction, and that's the key difference.
And then there's acceleration. Now, most of us think this just means hitting the gas, right? Speeding up. But in physics, it's any change in your velocity. And since velocity includes direction, that means even if your speed is totally constant, if you're turning, like a sprinter running the curve on a track, you are accelerating. It's any change, period.
So here's a quick look at the language we'll be using. These are the basic terms, the building blocks for motion in a straight line. With these in our back pocket, we are ready to dive into the really cool stuff, Newton's laws.
All right, we've got the vocabulary down. Now it's time for the main event, Sir Isaac Newton's 3 laws of motion. And look, these aren't just some dusty rules in a textbook. These laws are the invisible operating system that runs every single play, in every single sport.
So let's start with this. A hockey puck, just sitting there on the ice. Why doesn't it just start moving by itself? And then, once a player smacks it, why does it glide so far, so smoothly? The answer to both those questions is Newton's first law.
And here it is, the law of inertia. Basically, things like to keep doing what they're already doing. That puck stays put because the forces on it are balanced. It only moves when an unbalanced force, that hockey stick, comes along and changes things. It's so simple, but it's also really profound when you think about it.
So this idea of inertia is really just an object's resistance to change. You could almost think of it as laziness. Something heavy has a lot of inertia, so it's tough to get it moving. But once it is moving, that same inertia makes it really tough to stop.
And that leads us right into the second law. This is something you already know instinctively, right? You've got to kick a soccer ball way, way harder than you'd have to hit a ping pong ball to get it to fly off at the same speed. Well, that relationship between how hard you hit something, how heavy it is, and how fast it takes off, that's Newton's second law in a nutshell.
And there it is, maybe the most famous equation in all of physics. F equals ma. Force equals mass times acceleration. So what does this mean for an athlete? It's a trade-off. If you want to accelerate faster, you can either generate more force with your muscles, or you can have less mass. It's that simple.
And check this out. For an event like the shot put, it's not just about one explosive burst of force. To get that shot to fly as far as possible, the athlete applies a massive force for as long as they possibly can through their movement. That combo of force and time is called impulse, and it's a perfect real-world example of the second law.
Okay, now for the third law, and this one messes with people's heads a little bit. When a swimmer pushes off the wall, what's actually making them move forward? Is it their push? Nope, it's the wall pushing back on them. Wild, right?
This is the famous action-reaction law. For every single push or pull, there's an equal and opposite push or pull happening at the exact same instant. The swimmer pushes the wall, and the wall pushes the swimmer. That reaction force is literally what allows us to move. It's how we run, it's how we jump, it's how we swim.
So we've covered things moving in a straight line. But let's be real. Some of the most spectacular moments in sports involve spinning, flipping, and twisting. To get our heads around that, we need to leave the straight line behind and enter the world of angular motion.
All angular motion means is rotation around an axis. Just picture a figure skater pulling into a tight spin, a diver doing a somersault, or a quarterback putting a perfect spiral on a football. All of those are just incredible displays of angular motion.
So here's a puzzle for you. Look at this gymnast. They launch off the vault, and they're spinning, right? But then in midair, with nothing to push off of, they tuck their body in tight, and suddenly their spin gets way, way faster. How do they do that? There's no secret engine. What's going on? Well, the secret is a principle called the conservation of angular momentum, and it all comes down to this little equation. See, once that gymnast is airborne, their total angular momentum, that's L, is fixed. It's not going to change, but that momentum is made of two parts, their moment of inertia, I, and their angular velocity, omega. It's like a seesaw. If you make one side go down, the other side has to go up to stay balanced.
So let's break that down. Moment of inertia, that's I, is basically how much something resists being spun. When the gymnast has their arms and legs out wide, their mass is spread out, so their moment of inertia is really high. But when they pull everything in, when they tuck, they bring all that mass closer to their center of rotation. This makes their moment of inertia plummet. And because their total momentum has to stay the same, their angular velocity, their spin speed, has no choice but to skyrocket. That's the secret.
Okay, so this is all really fascinating theory, but what's the point? How does knowing any of this stuff actually make you a better athlete? Well, this is where we turn physics into a real, tangible competitive advantage. This is how a coach can use these laws to train smarter.
Look at this. These are 4 coaching points taken directly from Newton's playbook. Mastering inertia, that's about being efficient with your energy. Maximizing force, that's about your power-to-weight ratio. Harnessing action-reaction, that's about using the ground to your advantage. And increasing impulse, it's about applying that force over a longer period. This is literally a training manual written by physics.
So we started with that amazing high jumper who looked like they were breaking the laws of gravity, but now we know they weren't breaking the rules, they were mastering them. By understanding inertia and acceleration and momentum, athletes and coaches are pushing the boundaries of what we thought was humanly possible. Which just leaves one question really. Now that we know the rules, what new limits are we going to break next?